What we are doing now is we are continuing on logic minimization. What we have done so far is we talked about some ad hoc methods. We took a few gates and moved them around and did what we could do. Then we said this is not the way we can deal with large circuits. So let's come up with something more solid to be able to manipulate circuits that way. So what we came up with was Boolean algebra. So we defined certain rules and certain theorems, and then we said that okay, well, you can play with an equation, and that equation corresponds to a logic circuit, and then whatever you do with the equation, then it turns into the logic circuit, and that was good. So the thing that we did last was this example, which is really not a very huge example. And what we did was we started saying, okay, let's combine things together. Let's look to see what terms combine, what terms do not combine, and how we expand terms to make them combinable, as let's say. And so we, added the A bar to something, B bar to something. But, we had C, D, and is missing variables A and B. It's a 4-variable function. And then we said, okay, let's add B or B bar, okay? Why not A or A bar? And why not both? And so we really didn't have a very systematic way of doing this minimization. And then when we looked at the terms, we said, oh, okay, it looks like this one and this one match or can combine. And did a few things like this. And eventually we were able to come up with this expression. But then, is this enough? Is this the best we can do? I don't know. Okay. There may be other things that I could have done, which I have not done. And this could reduce even further. Okay. So, then what do we do? Well, what we do is instead of looking at these equations, let's come up with a way of graphically representing this expression. And if we do, then what term combines with what term? Hopefully we can see it graphically. And whether the final expression is the best we can do, well, maybe graphically we can justify the way we go through the graphical representation, and using the graphical representations, maybe we can do that. And that's exactly what we are doing now. We are doing Karnaugh Maps. Karnaugh Maps are way of representing circuits, and this way of representing circuit is a graphical representation. It corresponds exactly to Boolean algebra. I'm not doing anything new. All I'm doing is I'm taking the Boolean functions, representing them in a way that I can get a better insight into what combines with what. So far, we've been doing trial and error, exactly trial and error. If something we do comes up, reaches the end, and then we say, "Oh no, maybe I shouldn't have done this." Then we have to go back up, and whether we know how far back up we have to go, we really don't know that either. And whether we reach the minimal representation, I don't know. And no guidelines, just trial and error. And therefore, we need a graphical representation to smooth things out. And that graphical representation is called Karnaugh Map, named after a mathematician called Karnaugh. Unfortunately, I don't remember the year and the main reference right top of my head right now. So let's talk about Karnaugh Map. What you see here is a truth table. A truth table has output values for every combination of the inputs. Okay, and the inputs are 0, 0, 0, 1 because I have two inputs 1, 0, 1, 1. I'm only talking about a two variable Karnaugh map. I'm only talking about a two variable function. I'm talking about a two variable truth table. Okay, let's do the two variable. Let's use a two variable function and do all the definitions and all the properties of Karnaugh maps, and then we move up into more complex and larger Karnaugh maps and functions. So for now, all I'm trying to do is to familiarize you with the definitions. This is a truth table. That's one definition. This is a Karnaugh map. Karnaugh map means that it is the same as a truth table, except that truth table is a tabular list. Karnaugh map is a two-dimensional list. Okay, or is a two-dimensional table, sort of. Instead of having A and B as a list of the combinations, A and B are listed as A on the columns and B on the rows of the table. This table is a two-variable Karnaugh map. That's all there is to it. Okay? Now we will go through the properties to see how this simple representation can help us reduce functions. For A00, we have location 00. For A01, we have location 01. So each one of these correspond to the, so a row corresponds to a box. The yellow corresponds to the yellow box. Okay? And that's it. Now, if you want to number them, this is decimal number 0, 1, 2, 3. And then if you want to number the boxes in your Karnaugh map, that becomes 0. And then this becomes 1, this becomes 2, and this becomes 3. So if you want to memorize how a Karnaugh map is set up according to the rows of the truth table, this is the way. For now, I showed you what is a truth table, what is a Karnaugh map. And let's take a little function. This time, instead of the and, I'm going to take an or function. Okay? And let's say for now, I don't know if it's an or. And I'm going to show you the truth table and the corresponding Karnaugh map. Okay? Let's look at this and see how I can read my W output. I'm going to read my W output row by row. Okay? I start from the left-hand side. I say my W is, okay, for all those columns of W where it is a 1, I'm going to read it. My W is 1 if A is 0 and B is 1. I included every variable of my function in this term that I wrote. Do I have any more ones? Yes, I do. I have the next one. My output is 1 when A is 1 and B is 0. Okay? So my output is 1 if A bar B or if A B bar, right? Because when you read the table, you say, yeah, my output is 1 if A is 0, B is 1, or if A is 1, B is 0, or if A is 1, B is 1, right? This is how you read it. What did we come up with? We came up with these terms that are ORed together. These terms look like products. Okay, because we use dot for multiplication in regular algebra, and then this is like a product. So I call this one a product, this one a product, this one a product. I have 3 products representing my W. What are these products? What happens to these products? These products are summed together. Okay, it's not exactly sum, is ORing of Boolean algebra, but the operation we use, it looks like an add. And therefore I have products, and then I have sum of products. Okay, so this is a definition which I'm saying is a sum of products. All right. So this is product term. I have 3 product terms, each one corresponding to a row, and I'm going to show you the Karnaugh map here. A, B, 0, 1, 0, 1. A01 is one of them, A10 is the other, and A11 is the other. Okay? And this is this. This 1, 0. And then 0, 1. Okay? Each one of these circles in the Karnaugh map represent a product term. But then the way we read these product terms is we start from the left-hand side, and then we say that I have a 1 on W if A is 0 and B is 1. If I had another variable, I would say if A is 0, B is 1, and C is 0, for example. If I had another variable, I would read that also. And therefore, every product that I directly read from my truth table has all the variables of my function. Because this is the way I read, right? I say, okay, A is 0, B is 1, C is 0, D is 1, and therefore I say A bar, C bar, and form the product term. Then I say, if this is the way I obtain my product terms, meaning directly reading from the truth table, I call that product term a min term. M-I-N-T-E-R-M. And therefore, every product that you see over here, these 3 product terms, they are also the min terms of the function. I will also show you a product term that is not necessarily the min term. That's if you don't directly read from the truth table. By the way, reading the rows of the truth table has a correspondence to looking at the boxes of the Karnaugh map. Okay? So instead of saying, okay, let's read the orange line, orange row, then I could say, let's look at the orange box. The orange box has A, which is 0, B is 1, and therefore you could come up with the exact same product term if you look at this. This is A bar B. Okay? Then we have the green one. This is A B. And then we have the blue one. This is A B bar. All right? So, product term is anything one or more variables are ANDed together. That's a product term. A min term is a product term that has all the variables, usually obtained directly from reading rows of Karnaugh map or single boxes of the rows of the truth table or single boxes of the Karnaugh map. Summing them, that's a sum of product. Instead of summing them by writing A bar B, AB here, instead of summing it by doing this, I could just look up the numbers of the truth table, and those are the binary numbers of the corresponding rows of the truth table or the Karnaugh map. Let's do this. This is 0. This is a 1. This is a 2. This is a 3, considering A being most significant, B being least significant. And therefore, this is 0, this is 1, this is 2, this is 3. So instead of saying my sum of products is AB or AB bar or A bar B, let's just say my sum of products is sum of the min terms. That means single ones of the Karnaugh map. Okay? Single rows of the truth table. My sum of product is rows 1, 2, and 3. These are the rows for which the output is 1. So, you know product term, you know min term, you know sum of products. Okay? It turns out the sum of product I have shown you so far is also a standard sum of product. Anytime you have a sum of product where each product term is a min term, that is also called standard sum of product. Standard sum of product, it means that there is absolutely no other way you can represent it. So if you give it the whole class tries to come up with a sum of product, each product having all the variables, they all come up with the same thing. That's why it's called canonical standard sum of products. Canonical is Greek for standard. I can have sum of products that are not necessarily a standard. Look at this function here. This is a 3-variable function. And I am representing it as sum of products. This is one product. This is a second product. The first product has only one variable. The second product has 2 variables. Okay? And I don't have any product that has all 3 variables, and therefore this still qualifies for sum of products, but it doesn't qualify for standard sum of products. Okay? Even if I add a min term to it, because this is a min term, right? Even if I say A, B bar, C, okay, this third one is a min term. But the entire thing is not consisting of min terms only. Therefore, this is still called the sum of products. So anyway, you have products summed together, that's the sum of product. But if you have products that are formed by min terms only, that's the standard. Let me do this standard here. Okay? I read row by row. Y is A bar, B bar, C, ORed with. A, B bar, C bar, ORed with. A, B bar, C, ORed with. A, B, C bar, ORed with. A, B, C. If you really get tired of writing all of those, why don't you just write the numbers there? How about writing number 1, row number 1, 4, 5, 6, 7. This is standard sum of product for Y. This is standard sum of product for Y, because you are saying sum of min terms. This is sum of product for Y. This one, that was the original one, maybe this is minimal sum of product, but I'm not sure. Okay? All right, so we know products, sums, sum of products, min terms, and the standard sum of products. Okay? And we know, of course, Karnaugh maps. If you have a complex function and you want to be able to put or combine things together, Perhaps the easiest way would be to break it down into its little min terms. Okay? So the whole thing is clustered into several product terms, but then one product may contain something that the other product needs, and if you break it down into little pieces, then you can look at all these little pieces and say, oh, okay, now I can combine this together into smallest possible sum of product or minimal sum of product. So therefore, the easiest way to represent a function to start your minimization is represent the function in its standard sum of products. I don't really mean necessarily this. I also mean something like this, for example. See, when I say A, B, 0, 1, 0, 1, 1, 1, sorry, 1, 1, 1, okay? This is representing my function W in its smallest elements, min terms. Because I have 3 min terms, I'm showing it with 3 min terms. Now let's go back to Boolean and say, okay, I have this function AB or AB bar or A bar B. This is broken into its smallest little elements, these 3 product terms. Let's learn how these smallest little product terms are combined using Boolean algebra, using the functions that we have, or the rules that we have defined so far. Whatever we learn from there, let's go to, then we take those rules to the Karnaugh map and say, okay, the same way I did with the Boolean algebra, now I'm going to do with this Karnaugh map because they are both the same. See, this and this are exactly the same thing. The one on the left has W in terms of its smallest little products. The one on the right is the same thing. Okay, 3 ones here, 3 product terms there. All right, I start with AB, A bar B, AB bar. For no good reason at all, I like to combine, for no good reason at all, I like to write AB twice. Okay, I go back to my rules of Boolean algebra. Okay, yeah, there is a rule saying A or A is A or A or A or A is A. That means if I decide that I want A and B repeated 10 times, nobody stops me. Okay? Here, I'm not going that far. I'm only doing 2 terms, AB and AB again. Then I say, let's take the first and the third term. Okay? And then look at these 2 terms. They have B in common, but then we have A or A bar. B in common, but A or A bar. Let me do the other one also. And then I take these 2. These are, they have A in common, and then we have B or B bar. So, let's look at this. The first one and the third one. If I factor B out of this, this becomes A or A bar. The second one and the fourth one. If I factor A out of this, this becomes B or B bar. Okay? So the first rule I used of Boolean algebra is that AB is repeated twice. Then what I did distributive law on the first term, and the third term came up with this. On the second term and the fourth term came up with this. Now I'm going to use Boolean algebra again. A or A bar, Boolean algebra tells me it's 1, and therefore this becomes B and 1. Okay, B and 1. Boolean algebra tells me that A ended with B or B bar. B or B bar is also 1, so this becomes A and 1. Okay? Then Boolean algebra tells me B and 1 is just B, and therefore this is just B. And Boolean algebra tells me A and 1 is just plain A. Okay? And therefore what I'm coming up with is I'm coming up with A or B as the result of this. Well, we knew that already because we actually started with an OR gate, and now we are proving this is an OR gate. But what I did now is I represented the OR function in terms of its minterms. And then I used Boolean algebra rules to take those minterms and combine them into a product term that represents, or a sum of product form that represents my function in its minimal form. This is sum of products, but this is the standard sum of products. This is also sum of products because I have a sum and I have two product terms that are summed together. I used Boolean algebra to reach this. But then I also said something to you. I said that whatever I do in Boolean algebra, I should be able to do it in Karnaugh Map, because Karnaugh Map is no different than expressing a function in Boolean algebra anyway. Especially the two on top, that I have this Karnaugh Map on the right hand side, this Boolean expression on the left hand side. These are exactly the same. They're exactly the same thing. All right, so let's do whatever I did with the Boolean algebra. Let's do it with this Karnaugh Map here. I am taking AB and then ORing it with A bar B. Okay? So what I'm really doing is I'm saying, instead of individually circling these minterms, let's take these two minterms that are right next to each other. Look at this. I think that's a different color. No, this is the right color. All right, look at this. AB or with A bar B, that's the first term, first and the third term. The reason I could combine them was because these two terms have A, which is 0 in one, and 1 is in the other one. And therefore, by factoring B, A drops. So what I say is, why bother writing individual A bar B, A, B, and then applying Boolean algebra on it? Why not mapping these two ones that are on the same row, and on the same row meaning that they have a variable B in common and A is different, and then write all variables that are in common in these two minterms that are mapping. What are the variables that are the same in all the minterms that are mapping together? Well, there is only B. And then I do the same thing. I say, well, are there other adjacent ones that I can map? Yes, there are two adjacent ones over here. Then you say, wait a minute, you have already mapped that one on the bottom right hand side. I said, no problem. I can map a one as many times as you want. The same way I can write AB as many times as I want. And then this one is written as A. And therefore, instead of going through all this Boolean algebra, all this ANDing and ORing, and all the B and B bar is one and A is A, and instead of doing all of this, I said, well, let's just start from the Karnaugh map and play with the Karnaugh map and do whatever you do in Boolean algebra, but do it easier on the Karnaugh map. What I did was, let's go back here and then we go to the definitions there. Why was I able to combine AB and A bar B? That's because both of these are product terms. They have the same exact number of variables. And the only variable that is different between these two is B in one, B bar in the other one. I call products like this as adjacent terms. Let's do another one. I have A ended with B, or ended with C, and C bar ended with D. And then I have another one, A ended with B, ended with C, ended with D. This is a product term, this is a product term. Both of them have 4 variables. 3 of the variables are exactly the same. A, B, and D are the same. C in one is C, in the other one is C bar. Okay? Without really thinking much about it, I know that if I just take A, B, D, and then write C or C bar, I know I can combine these two into one product term, dropping C. So I make this definition. If there are 2 product terms having the same exact number of variables, one variable in these 3 is complemented in one, non-complemented in the other one, these 2 product terms that I refer to as adjacent, these 2 product terms combine into one product term, dropping the variable that's different in the 2. Okay? Name any product term here. A, B, W, not this W, some other W, Y, bar, E, that's one. A, B bar, Y, W, Y bar, E. Okay? These are adjacent. Same number of variables. There is only one variable that's different, B. Combine them and drop B. Combine them and drop B. Don't write any Boolean expressions. Don't apply any Boolean rule because you have already done this. So this is Boolean adjacency. My Boolean adjacency corresponds to my Karnaugh map adjacency, which I refer to as physical adjacency. I say that if there are 2 minterms along the same row, or 2 minterms along the same column, those 2 minterms are adjacent. And if they are adjacent, instead of individually mapping them, let's map the 2 together, the 2 adjacent ones together, and only write the variables that are the same in the 2 ones that you are mapping together. And that's exactly what I did with the horizontal map. This one here. I wrote it as B. And the vertical map, I wrote it as A, because A is the only variable that is the same in all these adjacent ones in this Karnaugh map. The great thing about Karnaugh map is this: Boolean adjacency and physical adjacency correspond to the same thing. Look at this. This is a Karnaugh map. A, B, 0, 1, 0, 1, this. Are these adjacent? No, they're not. Because I say adjacency is if they are along the same row or along the same column. So these are not adjacent. Okay. How about Boolean? Well, Boolean, they are not adjacent either, because this one is A bar, B bar. This one is A, B. They are different in two variables, so they are not adjacent. Therefore, physical adjacency and Boolean adjacency are the same. Okay, and instead of doing all this Boolean algebra, just go to the Karnaugh map and get it done with. All right. Next. This is what we said. Sum of product is good, but then working with the sum of products, there are too many terms to combine and all that, and therefore what we do, we define adjacency. In Boolean algebra, we call them Boolean adjacency, and then we say Karnaugh map has the same adjacency as the Boolean adjacency. So let's map the mean terms of the Karnaugh map instead of doing Boolean algebra. But then something else is going to happen later on. Later on, my maps are going to get bigger and bigger, and my adjacencies are going to change. Definition of adjacency. Boolean adjacency is not going to change, but corresponding Karnaugh map adjacency, which is what we call physical adjacency. With Boolean adjacency, we may need to modify our physical adjacency definitions a little bit. Okay, we get to that. But then, remember this all the time. Physical adjacency in Karnaugh maps corresponds to exactly Boolean adjacency in Boolean algebra. Let's do more definitions. This function has three product terms. These are sum of products, and these are the standard sum of products. Okay? This is standard sum of products. This function has A bar B that makes it a 1. So if A bar B is 1, W is 1. This function has A B bar that if this is a 1, that's a 1. This function has A B that if that is a 1, that's also a 1. This function has A, which if it is a 1, that function is a 1. This function, let me use commas instead of ors, has a term B that if that becomes a 1, function becomes a 1. So I'm saying A, B, A bar B, A B bar, A B, they all imply my function. And therefore, I refer to these terms as implicants of my function. So any term that it becoming a 1, my function becomes a 1, that's an implicant of the function. So that's an implicant of the function. Karnaugh map. AB, sorry. AB, 0, 1, 0, 1, 1, 1, 1, that's the same thing. This is an implicant of the function. This is an implicant of the function. This is an implicant of the function. Okay? Because if that becomes 1, my function becomes 1. This is an implicant of the function, because if this becomes 1, so will my function. This is an implicant of the function, because if that becomes 1, my function becomes 1. And therefore, I have 5 implicants in this function. In this function, 2 of my implicants are not completely covered by any other implicant, the green and the red. The black ones are all completely covered by upper level implicants, but the green and the red, They do have overlap, but they're not completely covered by anyone larger than that. And therefore, I refer to the green and the red as prime implicant. So the definition of prime implicant is this. If I have an implicant that covers an implicant that is not completely covered by another implicant, that's a prime implicant. Here's a third definition. Forget about the implicant. Now I'm talking about prime implicants. If I have a prime implicant that has at least a mean term, and that mean term is not covered by any other prime implicant, that becomes an essential prime implicant. Look at the green one. The green one has a the green one has a 1 here. I put a star next to it. That this one is not covered by any other prime implicant. You might say, well, wait a minute, there is this black one that is covering it. No, the black one is an implicant, not a prime implicant. I'm talking about a mean term not covered by absolutely any other prime implicant. If a prime implicant has at least one of these, then that becomes an essential prime implicant. And therefore, the green is essential EPI. And then I look at the red one. The red one has a one on the bottom right that is also covered by the green prime implicant. That one, this one, does not qualify my prime implicant as an essential. So I should look elsewhere. But then the one on top, true, an implicant covers it, but no other prime implicant other than the red one covers it, and therefore this one qualifies my red prime implicant as it being an essential, and therefore this is also EPI. So we defined implicants. Everything is implicant. Any 2 ones you can combine, any 4 ones you can combine, any single one you can see in your map, that is an implicant. Combine them into upper level, those become prime implicants. And then you go up, you say, well, this prime implicant is kind of a special because no other prime implicant covers this single one that it has, so that becomes an essential. Not all prime implicants are necessarily essential. How do I go about minimizing a function? First, I identify all prime implicants. Don't worry about identifying implicants. Implicants are cheap. They are everywhere. Okay? And then take this here. Let's identify prime implicants. Here is a prime implicant I identified. Okay. Here is a prime implicant I identified. Okay. So, since they're already marked, I just do this. These are already identified. This is done. Then, try to find the essential ones. Okay, try to find the essential ones. This one is essential, as we said before. This one is, say, this is essential because of that mean term. And then this is essential because of this mean term. Okay. So I found my essential prime implicants. Then it says minimal realization of the function is first list all your essential prime implicants. Okay, I have an essential prime implicant which is B, and then I have another essential prime implicant which is this one over here, which is A. Then go back and look to see what mean terms these essential prime implicants cover. B covers this and this. A covers this and this. Okay? And then look to see if you have, then look to see if you have any uncovered mean terms. I look here and I see that not only I don't have any uncovered mean terms, but one of my mean terms is covered twice, which is no problem. And therefore, at this point you say, well, this is the minimal realization of my function. But then you say, what if you do all the essentials and then you find, here is a mean term not covered by any of the essentials. And then you go into your prime implicants. You say, well, I didn't use all the prime implicants. I only used the essential ones. But let's look at the prime implicants that cover that mean term. And if you have multiple mean terms, then you try to find prime implicants that cover the most number of uncovered mean terms. We are not going to be seeing this in this two-variable map, but we will be seeing it in three-variable maps, which we'll be seeing next. Okay.